Welcome to CPE 329. I'm going to talk about timers and counters today. At the end of this lecture, you should probably be able to understand the benefits and drawbacks of using software delays versus timers, and then also understand the different modes of timers. So software delays are oftentimes inaccurate. Some of the reasons is that we can't control the execution down to a single clock. There is also, if we think about the assembly of code, it's essentially executing a whole bunch of assembly instructions called no-ops or no operations in a loop, and so there's some loop initialization that may add some error. And then also, I guess the biggest thing is that when we're executing no-ops, we can't power down the processor, we can't go to a low power mode. And also, we don't know about asynchronous events. An asynchronous event like an interrupt could happen in the middle of our software delay loop or our busy loop. And you know, the assembly code doesn't know that the interrupt happens, so the delay may not be accurate. So to solve this problem, what we have in the microcontrollers, most microcontrollers have several different timers. A timer is a simple counter, and it can either typically they count up and down, and they have very deterministic timing and far more predictable than software busy loops. They also have multiple modes. Apparently I wrote pulse width modulation twice here, but they can also do things like measure periods and also count the number of events that have happened. So at the heart of the timer is timers. At the heart of it, though, timers, what they do is they increment or decrement based on a clock cycle. And sometimes we can load an initial count or a compare value, and we can also reload the counter automatically once the counting is done to generate periodic events. So we can use this to generate timing intervals, measure timing intervals, or create pulse width modulated outputs. And we'll talk about that. So inside a timer is a counter itself, like the CPE 229 style counter, increments or decrements. Depending on the mode, and it can also, the counter can also do other things. Potentially, it could count like how many times a button is pushed, for instance. So if you push a button, it increments the count, for instance. You could imagine the hardware would look like this. This would be like a 229 hardware diagram here. In here we have a register. The register holds some value. It's an n-bit register here. And to it we're going to add either this is all 1, so it's -1 and 2's complement, or this is 1. So we can either increment or decrement through the adder. We're going to so the register value will go up or down. We could maybe load the register with some initial value sometimes, and then we can also the clock here could go through a block called a prescaler, and the prescaler, what it allows us to do is maybe divide down the clock so that this fast clock could be a slow clock, and then we could have a larger count dynamic range. And then there's usually some other functions like, okay, we can test to see if the register here has reached its maximum value, or maybe it's if the value is all 0. In the ATmega, this is their block diagram for the ATmega timer, so you can see it's a fair bit more complex. In theirs, they have, again, this register here. It's a timer, it's a count, and it either counts up or down depending on this control logic here that you can set up. And what they do is they can have it compare against a value in a register. So you program this a value into this register or this register, and when this value is equal to this value or this value is equal to this value, we can have something happen like an interrupt be generated. So also, if we wanted to count values, if we want to count like button presses, what we can do is we can attach a button over here, and the button will make the logic level go high, and that kind of goes into this timer here and increments the timer once. The other things we can do is like pulse width generation, and we'll talk about that a bit more, but we can see here that there's 2 outputs for this timer. Okay, so now let's look at a few sources of error even within timers. I guess the first thing is, let's pretend we had a 32-bit timer, so it could count up to 2 to the 32 minus 1. And we have a 50 megahertz clock going into this timer. That means that we have 50 million clock ticks per second. And the question is, can we count an interval for 1 second using a 32-bit timer on a 50 megahertz clock. And if we do the math here, we the max count in 32 bits is 2 to the 32, or 4 billion, which is greater than 50 million. So therefore, yes, we can count 1 second intervals. And so in a timer, in general, what you'd do is you'd load a register to 50,000 and set the timer to count down. Maybe enable interrupts, so once the timer reaches 0, generate an interrupt, and then enable the timer. Okay. Well, for the ATmega 328, there is a 16-bit timer, and let's say it's running at 8 megahertz. We're going to repeat the same previous slide just for this particular processor, and we say, okay, so at 8 megahertz there's going to be 8 million cycles, and for a 16-bit timer we can count up to 64K, or 65,535, and that's less than 8 million. So unfortunately we can't count using this timer and this input clock frequency a 1 second interval. So what we can do is we can count the number of overflows of this timer in software. So every time we get this thing overflows it counts up to 65,000 or 64K. We increment some software variable by 1, and we can count 122 of those. Okay. Now note that there's going to be some error here. So if we look at the amount of error per second there, well, okay, so there's 1 second, and we're going to subtract off 122 rollovers of the 16-bit timer at 8 megahertz, which is 125 nanoseconds. And what we find that per second we're going to get 576 microseconds of error per second. Not a whole lot, but it adds up, right? So if we multiply this out for an entire day, then we're off by about 50 seconds per day. And then in a month we're off by 2 hours and 29 minutes. So obviously there is some limitation here. Okay. So if we analyze the sources of error, well, right now we're not getting any error from invoking an interrupt. An interrupt is really just a latency, but it won't affect the periodicity of the timer. The code optimization, well, if we had software delay loops, code optimization could actually impact our software delay loop if it was poorly written. But in general, no. Since the counting is being done done in hardware in a timer, then yeah, that's not going to have any impact. The number of clock cycles per second, yes, of course that matters, and the number of the oscillator frequency also matters in terms of the accuracy of the timer. Okay, timers can also do other things. We can also measure, let's say, a pulse width. So here we see a pulse width here in the middle. And so what we'll notice is, okay, when the pulse goes high, what we can do is we can read the value. We can read the value in tcount1, and then when it goes low, we can read it and put it into tcount2. And what we do is we just subtract the 2 and we multiply it by the clock cycle, and that'll determine how many clock cycles have gone by between 2 events. So just a pretty standard thing to do. In some timers, we'll have this mode as a configuration setting for the timer. In others, you'll have to do this in software by yourself. So let's say we have this scenario where we have a 4-bit timer, and it's set to free run at 50 megahertz. And so if we had this situation before where we had tcount1 was 13 and tcount2 is 4, what we can do is we can subtract, right? Since this is less than this, we can subtract 13 from 4, and then we know that it rolled over. So then, if it's a 4-bit timer, we know 2 to the 4 is 16, and we do this math here. That'll be the number of timer periods that has gone by, and we're going to figure out, since it's using a 50 megahertz clock, we divide that through, and we come up with the pulse width of 140 nanoseconds. Of course, this is not the only possible answer, because actually what could happen is that rather than have this roll over once, it could be twice, or 3 times, 4 times. It could roll over multiple times, and so you have to be a little bit careful of that, right? It's either going to be 140 nanoseconds or another 16 clock cycles beyond that, right? Or some multiple of 16 clock cycles. Most timers also have a mode that allows you to generate pulse width modulated outputs, and this is one of the reasons why, if you go back to the architecture, the block diagram slide of the ATmega, you saw that there are two compare values. What they're doing is they're using a single timer and two compare values to allow them to enable the timer to automatically generate pulse width generation mode. What's going to happen is that one value is going to count how long the pulse is high, and the other one's the period, basically determining when to go high again. So this one is controlling when to toggle some pin high, and this one is actually counting down to figure out when to put the pin low. Okay, and PWM is used quite a bit. We have actually a tutorial on it later in this class, but it can be used to control the power. The power transmitted to something like a DC motor or an LED. Just for completeness sake, there is something called a Watchdog Timer. The Watchdog Timer is a special type of timer. You can kind of think of it as an hourglass, and if the hourglass expires, what it'll do is it'll generate an interrupt or maybe reset your processor for you. So basically, what you'll need to do is periodically you'll need to reset the Watchdog Timer if you have it enabled. And the reason we have this is generating deadlock-free systems is very tricky sometimes, and so a Watchdog Timer can actually break us from a deadlock setting. Okay, so for the ATmega 328, there are three basic modes of operation. There's overflow, compare, match. Basically, having the timer generate an interrupt or some event when the timer reaches either some value or overflows. And there's actually, in the 328, there are 8-bit timers and 16-bit timers. So when it overflows, it could either be after 64K events or 256 events. And then one nice thing about the ATmega 328 is that there's different prescalers that we can use as well. That range from 1 up to 1024, so you can divide your system clock down by 1,000 before even sending it to the timer. And that also allows there's an asynchronous mode as well, where you could use the timer's clock source could come from outside the chip. Of course, you have to provide it a clock then. It also has an input capture mode. It can count the period, count the amount of time between times when the pin went high or something like that. And then it also has pulse width mode, and we talked about that. Okay. There are a few registers that are associated with the timer. So there's timer control register A and timer control register B. And N here is the timer number. So I think in the 328P there's timer 0, timer 1, and so this would be TCC R0A and TCC R1A for timers 0 and 1 respectively. So these are control registers, and it just sets the mode of the timer. There's also a timer count register. It's the actual count value. It's counting up, 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 up. And this is these are output compare registers. This is when this is equal to this, then we can generate an interrupt, for instance, or this equal to this would generate a different interrupt. To control interrupts, we have a mask register. Basically, it allows you to enable or disable individual timer interrupts, as well as a flag register, which allows you to check to see if an interrupt was created in software. Okay, so I don't pretend that this lecture is completely self-explanatory. The best way to learn this stuff is actually to go ahead and do your assignment. And so the assignment is at the end of the timer interrupt tutorial, so go ahead and download that and work on that now. But there's also an ATmel has created a timer app note that also has some sample code in it that could be worth a read.